Hello, my name is Sarah Astles. I'm the CEO of the International Space Federation. Thank you for joining us today. Nassim Haramain is joined by Dr. Olivier Alaral and Dr. Cyprian Gorman-Prey. Over the next 2 hours, they will review the recently released paper, The Origin of Mass and the Nature of Gravity. After the 2-hour presentation, there will be a 1-hour question and answer period. They're looking forward to hearing your insights and questions. Thank you, and enjoy the presentation.
Hello, everybody. So glad to be with you on this technical seminar and the release of this new paper that is just right out of the oven. I'm here with Olivier Alaral.
Hello, everyone.
Alaral, and with Dr. Cyprien Gorman-Prey. And we're going to present to you and review this paper that we actually just published a day and a half ago on the Zenodo platform, which is the preprint platform of CERN. And we're really excited to share it with you. We're excited to hear your comments and your thoughts on it, and really to discuss it together and learn and grow together as we define more deeply the origin of mass and the nature of gravity. And so there is a lot of material. We did the French one yesterday and we ran out of time, so we're gonna try to do better tonight and really get in there. This is a new interface that you might not be familiar with. So there's a few things. There is a chat that you can find, correct? On the right-hand side?
Yes, on the right-hand side of the platform.
On the right-hand side of the platform. If you close the chat, if you want a full screen, you got to close the chat and you'll see a little full screen icon on the right. And you can click that and it will go full screen. And then there's as well a place where you can ask questions. So you can place your questions in the question part, which is right below the chat.
Yes.
And they'll get voted on, and we'll pick the questions that are getting the most votes, correct?
Yes, exactly.
So we're going to start with 2 hours of presentation of this paper. There's a lot of material. It's a fairly long paper. It actually is a part of some 400 pages of manuscript that we've wrote, and that we finally came to the concept that we need to cut it in pieces. And so this is the piece. It's a fundamental piece of it, but it is a piece and it needs the rest as well. So I'm sure you'll have a lot of questions about other parts that we don't address in this paper. It will be part of a series, so I'm hoping that you will be there with us along this series of papers released that will occur in the next year and a half, so in the next few months, and then again, and so on. And every time we will have a session like that so we can discuss the paper and we can move forward together. So without ado, let's start with the presentation and the origin of mass and the nature of gravity.
Yes, exactly. So we are going to start with the introduction. So the idea of this technical workshop is to do the full reading of the paper and to guide you into the reading such that you understand all the major concepts and the major equation of the paper, so that you can read it again and maybe go a little bit deeper into the understanding of the paper. So we have 2 hours of a presentation and 1 hour of questions, and do not hesitate to put any of the question in the Q&A section, like Nassim said. And now we start with the nature of mass and the origin of mass and the nature of gravity. So we start from the observation of the fact that general relativity state a major point, saying that the mass relating the mass energy to the structure of spacetime, and this relationship is associated to strong gravitational interaction responsible for the organization of matter at very large scale. And on the other side, when we apply this gravitational interaction or the gravitational force to the very small scale at the particle level, the interaction seems to be very weak. And on the other hand, at the particle level, we have strong interaction related to very high energy, responsible for the proton stability and the proton structure.
The confining forces.
The confining forces between the quarks.
Mm-hmm.
And we decided to ask the question, why is, instead of saying, why is the gravity so weak at the particle level, it's maybe better to say, why is the proton mass so small?
Exactly.
And this is a good example of why it is very important to ask the right question to find the right answer.
Exactly. Which is a question that Frank Wilczek asked earlier as well, and many others. But it's commonly, I think, in the intro. So here we're describing what's in the intro of the paper. We're trying to give a sense to the reader as well that there is a tendency, we put things in boxes. And then we forget that we've put them in boxes.
Yes.
And the tendency is to think that mass is some kind of value that's fixed, that is, unmutable. And really, since the early 1900s, with special relativity and then eventually general relativity, mass has been shown to actually be, first of all, equivalent to energy, and to have effects on the structure of space-time. And so when you put that all together and you look at the way mass is treated at the quantum level as well, you find that mass is actually something that can be described in a much more fluid way. Mm-hmm. Than something that's immutable, that's a fundamental, characteristic of something, mm-hmm. and that cannot change. Like actually, if you accelerate it, it can, and so on. And at the particular level, there's this thing that's called bare mass, mm-hmm. Which emerged from the equations of quantum physics, and we'll see details about that. But that describes the mass as something very, very high in energy, mm-hmm. At the particular level, mm-hmm. that has to be screened by vacuum fluctuations. Mm-hmm. So it's called dressed mass, right? It goes from bare mass to dressed mm-hmm. mass, so that actually what we measure is not the bare or the naked mass, but we're measuring like a residual effect of the mass, mm-hmm. of the bare mass, mm-hmm. that's being screened by vacuum fluctuations.
Yes, exactly.
And another important point that we will explore is the link between mass and gravity. Because it's not obvious for everyone, but for example, the Standard Model found the mass with the Higgs mechanism, but they didn't find the gravity at the same level. Mm-hmm. Showing that the link in their equation is missing between mass and gravity.
Correct. And the Higgs mechanism, which has a non-zero vacuum value, thus emerge from some fluctuation of the vacuum of the Higgs field, mm-hmm. Actually only predicts 1% of the mass of the proton, of the quarks, yeah, and which makes up the proton.
You are right. Sorry.
Yeah.
Of the proton, 1% of the proton.
Yeah.
Predict the mass of the quarks, which constitutes only 1% of the mass of the proton.
Yeah. And the other part of the mass in the standard model comes from the strong force, comes from confinement force that provides the energy for the proton mass. And the proton is the mass of the universe. The universe mass is the number of protons in the universe. And then at the universal level, we're missing dark energy and dark matter. And so we only predict 4% of the mass at the universal levels. So between, the Higgs mechanism only predicting 1% of the proton, and then dark matter and dark energy only missing and only predicting 4% of the baryonic mass in the universe, we end up with less than 0.1% of the mass being predicted by standard theory. So mass is physicists do this every day, talk about mass, they talk about forces, they teach it every day, and it kind of becomes this habit of thinking that the mass is some kind of immutable thing. And in the introduction, we're kind of dispelling that, and we start, looking at what would be the source of mass.
Yes, exactly. And another key point of the introduction and that you mentioned earlier, Nassim, is also that the zero-point energy, which is the energy of the electromagnetic quantum vacuum fluctuations, is predicted by most of the theoretical physics, meaning quantum electrodynamics, quantum chromodynamics use this vacuum as a source of energy to create and annihilate particles. So the objective of the paper was to can we merge the high gravitational interaction of general relativity with the high energy of the strong interaction at the particle level and combine them thanks to the vacuum fluctuations. And this is why we decided in the first part of the paper to go back at the root of the physics of the early 90s to understand what is the zero-point energy, how has it been discovered, and also to study the physicality of it, because it was a rather theoretical concept at the beginning, but then physicists found that it was necessary for the mathematical consistency of quantum mechanics, and they also found it as necessary to explain some of the effect that we observe at the particle level.
Exactly. A little bit like black holes in cosmology were thought to be really theoretical objects that probably didn't exist until, the late 80s, early 90s, and so on. And then we started to find them, and then they became fundamental to cosmology. And I think that as well, like what Cyprien was saying is important, because Cyprien was utilizing the terminology strong gravitational forces or strong gravitational components. And so it's important to remember that while we have this general concept that gravity is weak, at the same time, we have this really obvious evidence of very, very strong gravity in certain circumstances, namely in black holes.
Near black hole horizons.
In black holes horizons and in these circumstances. So you can look at it and look at the equations of relativity and say, well, okay, yeah, gravity can be really strong when you have a large density of energy on the stress energy tensor side, on the mass side of the equation. But what is that? Where is that coming from? Where is that energy coming from? Is it just accumulation of protons in a region of space, or is there dynamic of space itself that's producing this effect?
Yeah.
And so it starts to, you start to think, and now I'm kind of blowing through stops, but so I should stop talking. But basically, you start to think that you know, it's not just the source, mass, energy, that curves space-time, but that space-time effects actually produce mass energy on the other side of the equation. So you close the loop a little bit on Einstein field equations. All right, let's get into it.
Yes, let's get into it. So just to finish the summary of the paper so that you have the big picture. So after reviewing the zero-point energy and calculating its intensity, and we will investigate the impact of this zero-point energy on the structure of space-time and how we can use this impact on the structure of space-time to define a way to explain how mass and forces are generated out of this vacuum fluctuations. And finally, we will investigate how the study of the particles can lead to larger scale studies and larger scale understanding of the generation of mass and forces. So now we can dive into the paper.
Yeah.
Yep. So here's the paper, and we've scrolled down to section 1, and the section 1 starts with zero-point energy and its consequences and you know, the origin of the discovery. So, you know, we start with the most obvious start.
Starting from black body radiation.
Body radiation. So that's Max Planck. So maybe a little bit of history on black body.
Yeah. So initially, when they started to study the black body radiation, Stefan Boltzmann defined a law linking the electromagnetic energy radiation from a hot black body, giving the energy flux in terms of the temperature of the black body. And this is the Stefan Boltzmann law given in equation 1.1. And the goal at its epoch was to explain the measured energy density spectrum and avoiding what was called at the epoch the UV catastrophe.
Yeah, the ultraviolet catastrophe, where the classical theory of the time predicted that the ultraviolet emission of a black body would
be infinite.
It diverged to infinity.
Yes, which didn't match the measurement of the 90s of the experiments predicting finite emission at the UV
of the UV. So just to be clear, about a black body is a thought experiment, but it relates directly to like the filament of a light bulb, if you'd like.
Or any matter is emitting as a black body.
Actually,
even if it's not black.
Yes, even if it's not black.
Yeah, which was very interesting at that time is that they start to send light to the matter to understand the interaction between electromagnetism and the matter. And by doing that, I think they start to investigate the structure of the atom. And this is what Max Planck tried to do, to find how an atom would react to electromagnetism. So he decided to use the model of an harmonic oscillator to describe the rotation of the atom. And this is what the dynamics,
like the fluctuations of the material world that would emit thermodynamically, and the spectrum that emits thermodynamically.
Yes.
And so the perfect emitter would be a perfect absorber, right? So so thus the concept of a black body. Interestingly, you know, a black hole cosmologically is almost a perfect black body, and so it's an interesting concept. Yes, like a star, like our sun, and so on. And so here we actually, in the first figure, right from the start, we try to dispel a little bit some of the concepts that are, you know, being taught in universities every day to all students, and it's good. It's fine. However, we're wanting the reader to actually get the right visuals, because we've all been taught that you know, when you're talking about an oscillator, that you're either talking about a pendulum or a spring with a weight on the end of it. That's usually the analogy that's most given when you're learning the first step into quantum theory and so on. When you're talking about an oscillator, you're talking about a spring, a linear motion of a spring, you know, with a weight on it, and it's oscillating with zero dampening, right? And I think it's really important that although it's equivalent mathematically, that we actually get the right visuals in our head, because the universe is most likely not making atoms as little springs oscillating linearly in some kind of, you know, one-dimensional oscillation, but actually in a three-dimensional spin, which is equivalent, so you can get the right answer. But this is really important, and that's what I said yesterday on the French one, is that it's really important to understand that you can get the right answer with the wrong mechanism. And I think one of the most famous example was the heliocentric and geocentric solar system. When the geocentric solar system was the, you know, the way to think about our solar system at the time, it was very accurate. You could accurately predict the position of planets and everything in the firmament, and everything was fine, and there was no reason to want to change it, except that when you looked at the model of the solar system, it looked like a bad hair day, you know, like my hair in the morning, you know, it's a little bit crazy. And it's like, okay, but and then as soon as we went to heliocentric, we put the sun in the middle, all of a sudden it became simple, clear, and as well very accurate, actually more accurate. So it's really important to get the right model in our heads, and to actually, you know, think of it in the physicalness of the universe, not just like, oh, you know, let's, you know, get a spring and think of it that way. So that's why we did that. Okay, I'm taking way too much time, but it's really important.
So yeah, the important thing at that time was to determine what is the internal energy of the atom. So Planck made several assumptions, and he developed two different theories in order to predict what would be the internal energy of the atom. And those energy, we have listed them in the beginning of the paper. And as we saw with the first theory on equation 1.5, when we do the Taylor series of this internal energy, we realize that the energy is kT minus a half of h nu, meaning that when the temperature goes to zero, we have a negative internal energy, which was not possible at the time, but also it does not reduce to kT, which was predicted by the equipartition theorem of the 19th century, predicting that the energy of a system at high temperature, meaning at the temperature which means that kT is large before h nu, it does not reduce to that. There was this correcting residual term, and he didn't know what to do with this term.
Exactly.
And
this was really his second, you know, at first, Max Planck didn't he resolved directly to Stefan Boltzmann, but it was with further exploration that he discovered this second term that just emerged, and that was necessary for the equations to be consistent.
Yes, exactly. So the spectral density that he obtained with this internal energy provided the right prediction of the Stefan Boltzmann equation, but he didn't know what to do with this residual term.
Exactly. And so it's really important as well to dispel this, there's a little bit of like confusion about the nature of zero-point energy and that it's some kind of weird animal that, you can ignore generally because it's kind of out there, on the edge of physics. It's actually at the very base of quantum mechanics, and it is critical to most of what we found in quantum mechanics, and we're going to go through that in a little bit.
Yeah, so 10 years later, he developed his second theory, in which the internal energy, he had the first internal energy, he obtained the same one plus this 1/2 of h nu, which were called at that time the zero-point energy or the ground state energy of the system, meaning that when the temperature goes to zero, the remaining energy is this 1/2 of h nu. And he obtained the right answer for this internal energy, but in some way he mixed the first theory with the second one so that he could still have the Stefan Boltzmann law with the spectral density, and having the right answer for the internal energy. But more modern derivation demonstrated that the spectral density should also have this zero-point energy of 1/2 h nu. And when you integrate it on all the possible mode of the vacuum fluctuations, what we see on the equation 1.9, we obtain a divergent term unless we use a cutoff value.
Right. So this energy found, which should have been the ground state,
yes,
right,
exactly.
at 0 Kelvin, actually wasn't ground state at all, or it didn't seem like ground state. It had infinite amount of energy, like a field of infinite potential. And this divergence, so it's really interesting in some ways that he resolved the divergence of the UV catastrophe by resulting in a divergence of the electromagnetic field at the ground state. And that kind of like was something that was not treated very clearly from there on. I mean, Einstein and Otto Stern worked on it. They tried to understand it better. There was Nace later on that worked on it. And, oops, sorry, wrong mouse. So basically, in general, what happened in the centuries since is that in general the assumption has been made, and correct me if I'm wrong, that zero-point energy can be ignored, that it's chaotic, and as a result,
it's the ground state.
It's the ground state.
We can normalize it.
We can normalize it, so we start from there and we go up, and we're just gonna assume that it's completely incoherent, so it cancels all out, and we can call it zero. The problem with that approach is that it's inconsistent with the foundation, or like with mathematical foundation of quantum mechanics, right?
Yeah, it's both inconsistent with the mathematical of the quantum mechanics, as we will see with Dirac, but also with experiments. Because many experiments can also be explained by the presence, but the existence of the vacuum fluctuations.
And some of these experiments are critical, like the lamp shift,
or even the photoelectric effect,
or the photoelectric effects, and so on. And so actually 0 point just can't go away. And although, you know, we can teach physics every day to students and all this and say we can ignore that part, at the end of the day, if we're actually doing fundamental physics in quantum theory, that field is absolutely present and it's absolutely necessary for all the mathematical consistency of quantum theory.
Yes, and this is why we have added also the modern derivation of the zero-point energy, which start from the electromagnetic and electromagnetic field, and we realized that this zero-point energy arises when we have a coherent oscillation of the electric field, and the coherence calculation is shown in equation 1.12, and this part about the coherency is very important. We will see later how the mass will result from the state of coherence of the zero-point energy. So
I want to make sure we're all clear with the viewers right now. This is not, you know, unusual. This is straight up from, you know, physics,
Maxwell equations.
Maxwell's equation, physics books. You'll find it in all courses on quantum mechanics. This is nothing unusual. I mean, it's there, and it's fundamental.
Yeah, so
and we give all the references. I want to stress as well that this paper has 115 references, and many of them are critical, and people should take the time to go through the references and pull the papers and pull the books and look at them themselves.
Yeah. And what we see in this second subsection is that when we integrate all the modes of the electric field to get the electromagnetic energy density in equation 113, we can see that a first term arises as the Stefan-Boltzmann law, and the second term coming from the 1/2 of h nu that we saw earlier from the ground state. Is a diverging integral if we do not use a cutoff. But we'll see in the second section how we can choose a proper cutoff with our current state of physics. Yeah.
Okay.
And then we have investigated how the zero-point energy, like Nassim said earlier, is necessary for the mathematical consistency and how it is at the root of the quantum mechanics. And to do that, we started with the Hamiltonian of the harmonic oscillator.
Of the harmonic oscillator. So it's energy.
Yeah, so basically it's the potential energy and the kinetic energy. And it's very traditional in quantum mechanics to describe an oscillating system, especially in the perturbative theory, where we look at small variation around a state of equilibrium. And to solve this equation, Dirac developed a whole theory of operator, and he came with a new idea of annihilation and creation operators, such that the Hamiltonian can be transformed into the version of equation 116.
116. Here you can see the A dagger and the A, which is the operators of alienation and creation operators.
Yeah, which is very interesting. This name of creation and annihilation, because quantum vacuum fluctuations are often described as cycles of creation and annihilation of particles from the vacuum.
From the vacuum, typically called virtual particles, virtual photons. Yes.
But not only. Again, the photoelectric effect or the spontaneous emission of photons by atoms is directly linked to this vacuum from which emerge real photons, or real photons are absorbed by this vacuum.
Exactly. And
Yeah. In the Bohr model, so it is described several energy levels, and when an electron comes from one level to a lower level, it's supposed to emit a photon, and the photon comes from the vacuum fluctuations. So
yeah, or
And-
absorb a photon.
or absorb a photon.
Yeah.
And also, because it's quantum mechanics, the electrons can't go continuously from one level to the other. It needs to disappear and reappear to the next level.
Yeah, quantum tunneling and the dynamics of this energy exchange requires that ground state to make the exchange.
Yeah.
Yeah.
And so this ground state needs to be full of energy to be able to absorb and remit any particles,
Right.
which could be an electron or a photon or even a bigger particle.
So Dirac ended up with this kind of soup at the ground state of very dynamic creation. And I want to stress as well that when we say virtual, I know you know this seminar is for technical people, and I'm sure in general people know this, but I just want to remind people that it's called virtual not because it doesn't exist, but just because it has a very, very, very short lifetime. And so we don't experience it directly in the structure of the vacuum. Now, you know, that while is correct, is as well correct because the scale at which we experience the material world, and we'll see that a little later on.
Yeah.
So, so we do this calculation.
Yeah, of the eigenvalues of the Hamiltonian, such that we got the energy level. So this is very classical calculation. Everybody knows that once you've done quantum mechanics. But the important part is the 1/2 here that come from the 1/2 of h nu, corresponding to the 0-point energy of Max Planck. And this 1/2 is also very important because what we see here is when we look at the mean expectation value for the electromagnetic field, we find a 0 value, meaning that we cannot observe it. However, when we calculate the energy of the electric field, which is the mean value of the electric field squared, we find a non-zero value, meaning that there is a disposable, no, not disposable, available energy that remains, and disponible
in French. Yes.
and this energy has a physical reality. And what we have also shown in the following equation is that the 0-point energy can be seen as a source term, because when we look at an atom as an oscillator, as we saw earlier, so Einstein hoped develop a model to have the harmonic equation as in equation 1.23. And in this equation, what is interesting is that we have in the first term on the left-hand side, we have a x dot term, meaning that if we don't have the source term on the right-hand side with the E0 corresponding to the 0-point energy, we will have a damping of the harmonic oscillator, meaning that at some point we could expect that maybe the proton or the electron around the proton would stop its rotation.
Quite rapidly, actually.
Quite rapidly.
I don't think the universe would be anywhere close to existing.
Yes.
All the oscillators should have dampened a very long time ago, and our universe wouldn't be around. So there is a source term, and this is really important. That's really a concept that has to like emerge for us to in this paper that we utilize in this paper, and that we demonstrate the importance of this source term. It is there in the equations of quantum mechanics. It's required. It's there, and it's not really addressed fully.
Yes.
Say because it is critical for you know the oscillators to continue oscillating.
Yeah, and a way to observe that is what we've shown later, is when we look at the commutative rule between operators. And the commutative rule that we have explored is the x and p, momentum and position. And what we see is that the classical result of the commutator of x and p is I h bar, cannot be sustained without the zero-point energy. This is what this equation 1.27 is saying, and which is very disturbing. I mean, for me, it was very disturbing at the beginning, because for me, it was like a mathematical rule. So it's just the equation. Naturally, the EH bar should arise. But when we go back to the physics of the equation, we realized, thanks to the book of Miloni, that the zero-point energy was essential to maintain this non-commutativity of the operators.
For the consistency, for the mathematic consistency of the operators,
yes,
in quantum mechanics, the zero-point energy, the source term has to be there.
Yes.
Right? And so, you know, this was really an important point. You know, Cyprien's been with us for 8 months. He did a very high, steep learning curve during that time. Olivier and I have been working for 6 years together, 6 or so on. And so, but as well, like to actually break down the equation and extract and see what the equations are really saying. And this is something I wanted to discuss as well. Is that in this paper, we commonly do this. In this paper, it might irritate some physicists. We leave the equation open, or we open the equations. That is, we don't necessarily reduce, and we certainly don't remove the units by doing C equals H bar equals G equals 1.
Yeah.
You know, we keep the units, we keep the equation in a format where we can understand the mechanics
Yes.
of what's going on, and interpret these mechanics, which can lose its meaning when you mathematically reduce it to something that you don't know anymore. Like the terms are there, and you can play with it, but you don't know anymore what you're learning about the reality of the physics, you know, of the material reality that you're exploring.
Exactly. For example, here, the H bar, most of people forget that it's an angular momentum. I mean, so reminding the reader and the physicist that the oscillator, the harmonic oscillator, is a rotation due to this angular momentum energy. And another important part about this non-commutativity is that it's at the origin of the Heisenberg uncertainty principle, because without this this non-commutative rule, we cannot deduce the Heisenberg principle, and this is what we have put back. And it's an interesting point, because most of the time we can read in the literature that the vacuum fluctuation are due to the Heisenberg uncertainty. And in fact, it's the opposite. It's due to the vacuum fluctuation. We have this uncertainty principle
of the position and momentum of particle.
Yeah.
And you know, it's so common when you know, talk about zero-point energy or quantum vacuum fluctuation to someone, they say, yeah, it's due to, you know, Heisenberg uncertainty. You see it even in literature on the internet everywhere. And it, you know, it's partially correct, because you can, you know, turn the equation around and get there, but mechanically it comes directly from the operators of the structure of the vacuum. And so why is there uncertainty? Well, because if a particle is in a fluxing ground state, it's constantly being pushed around. Literally, it's constantly, interacting with the field. And so there is uncertainty about its position or its momentum and so on. So, but as well, importantly, what's critical there is that you can see that this mechanics like emerge in some ways in quantum field theory, in QFT, when Dirac was doing all this, right? And he started to think of it as like an ocean. Right, and that's why we start quoting Dirac later on and talking about Dirac because he thought of this fluctuation field as this sea of energy, the Dirac sea, is literally called that way, and from it he was able to predict something very real, which is the existence of antimatter. And
with the positron.
With the positron, which was eventually isolated and discovered. And so that was a really big confirmation of all of these mathematics that Dirac elucidated in quantum field theory.
Exactly. So after describing all this theoretical background about zero-point energy, we felt that it was important also to remind the reader that all the experimental validation of the zero-point energy, especially with the experiment of the lamp shift or even the Casimir effect. So in the lamp shift, it was a measurement by Lamb and Rutherford that measure a small perturbation of the energy level in the hydrogen atom predicted by the Bohr model.
And go ahead.
Yeah, and with the Casimir effect, it was a little bit different. It was about so Casimir realized in 1948 that when you put two mirrors very close, you could remove some of the vacuum modes between the plates, such that the additional mode from outside would push the two mirrors together, and this could be done only in a vacuum and by taking into account the zero-point energy.
Correct, and it was a very difficult experiment to realize because you had to put the plates microns apart. That means you had to be able to have plates with micron precision, which in 1948 was nowhere close to happening. And so it was all very theoretical, and that's why most physicists generally ignored it. And it took till the 90s, mid-90s, till we were able to put plates that close together, and we measured then that force applied to the plates by creating this little cavity, this little depression between the plates. So, then this was debated still, but the existence of vacuum fluctuations, although they're fundamental to quantum physics, and then eventually the dynamical Casimir effect, where actually the plates are oscillated at very high rate, and actually photons emerge.
They could create photons out of the vacuum.
So photons literally emerge from the vacuum, and then that was a very big confirmation moment. There was others. Lately, there's been Casimir torque, which is another very interesting way of thinking of it. But in every case, although it's a very, very small amount of energy, in the plates there's a force. In the other case, there's photons emitting. In a little torque. These things, we are actually seeing energetic effect at our scale, which is very, very far from that ground scale. That are occurring in our world.
Yeah, and actually there are many applications of the Casimir effect, like adhesive, because they reproduce what the gecko was doing biologically, meaning creating like very teeny Casimir effect, but a lot of them, and reaching a macroscopic effect from this microscopic force.
Object, you know,
Object,
like a gecko
like a gecko, yeah.
sticking to a ceiling.
Sticking to a ceiling or to a wall, and they reproduce it with like a robot being able to go on a wall vertically.
With these micro hairs
Micro eyes, yeah.
that ends up between the molecules and experiencing
Yeah,
Mendel
at
walls
the microscopic scale, yeah.
at the microscopic scale. Yeah. So there is all kinds of evidence now. Actually, there is evidence at the cosmological level as well with
Vacuum Beer refringence.
yeah, vacuum beer refringent that is like, you know, a polarization of the vacuum in very high magnetic fields, you know, pulsars or
yes, exactly.
yeah, and this, so there's many confirmation of this energy. Never mind that quantum physics requires it to be consistent.
Yes, exactly.
Right. So we go through this table a little bit, we talk about it, and then
we arrive to the second section where we started with the calculation of the zero-point energy, and one should notice the three that arise in the ground state in equation 2.1. The three arise because of we take into account a three-dimensional harmonic oscillator, so that we have to put a 3 there. And then we sum up all the modes.
So instead of just a linear spring,
yeah,
we're talking about
a sphere, a rotational sphere.
A rotational sphere.
And then we sum up all the modes in the continuous way, resulting in an integral. And the integral, as we said earlier, if we put an infinite amount of mode, will be infinite. And a way to have a finite value is to use a cutoff.
A finite value would require a cutoff.
A cutoff. So we investigated which would be this cutoff, and a way to do that is to look at the general relativity condition provided by the Schwarzschild radius, equation 2.5, and another condition brought by quantum mechanics by the Heisenberg uncertainty, meaning that we have a minimal angular momentum for the system. And by combining the two conditions of general relativity and quantum mechanics, we found that the minimal size of a system would be a system of the Planck length and with the Planck mass.
With the Planck mass. So the Planck length and the Planck mass emerge naturally from the combination of general relativity and quantum mechanics. And you know, we went over a little figure here that I love. This we've reproduced from Wheeler's
quantum foam
concept, where he was visualizing or describing what he was finding in his mathematics, which was, well, you know, why don't we experience the vacuum fluctuation if they're so intense, if they're so high? Because, you know, when they have a cutoff, even at the Planck scale, they're very energetic, and we'll see that in a minute. But it's because we're talking at billions and billions of billions of, you know, scales smaller than us. And so at that scale, from our scale, it appears smooth, like space-time appears smooth. And at the quantum level, just like if you're...
It appears smooth when it's not current, because it's appearing like curve, like matter, like protons.
Right, right. So when it's curving, then
it's not smooth anymore.
It's not smooth anymore, but that might sound a little strange what Olivier just said because you don't have the rest of the paper in your mind, but you'll see what we mean by that. But basically, this image is saying like so like just like if you're in space and you're looking at the surface of the ocean on the Earth, they could be 10-foot wave, they could be 20-foot waves, and you would have no idea. You would look at it, it would look smooth, right? It would look really good, really smooth and flat, right? I mean, other than the curvature of the Earth, but the ocean would look smooth. And so, but as you got closer and closer and closer, all of a sudden you'd realize, wow, there's so much energy happening. There's 20-foot waves and there's lots of energy, there's forces and all this that you would never know about if you weren't like focusing and like zooming in to see what's happening at that level. And when we use quantum mechanics, we're zooming in. And that's what we're finding, right? Yes. And Wheeler called it fluctuations of wormholes because the energy is so intense that space-time would be curled in very, very tight packets of wormholes and black hole dynamics. So this first approach to finding the cutoff is kind of like a little quick and heuristic.
Yes, exactly.
So we looked for a second confirmation to this approach.
Yeah, by using the work of Wheeler on the quantum foam, he used the Feynman path integral to investigate how the metric, which is responsible in general relativity for the gravitational interaction with electromagnetic energy, to see how the metric will respond to intense electromagnetic fluctuation, as in quantum vacuum fluctuations. And he found that to have a response of the metric, we need to have coherent interaction between the metric and the vacuum fluctuation, electromagnetic fluctuation, and this can occur only at the Planck scale level. This is why he came up with this idea of the quantum foam, which is made up of wormholes of Planck size and Planck mass and Planck charge. And he described the space-time, the structure of space-time and even particle from this coherent and disturbance of this wormhole C or quantum foam. And this is how we decided to use the Planck scale at the minimum scale, meaning that in the quantum oscillator, harmonic oscillator that we've talked earlier, it means that the smallest cavities that we can observe in our world is a Planck scale cavity. And this allowed us to calculate a finite expression for the vacuum energy density that we called ρvac throughout the paper, which is very important data because we mention ρvac all the time. And we found a value of 10 to 113 joule per cubic meter.
Right, so now we've jumped quite a bit.
Yes, yes.
We've jumped multiple concepts. You guys going to have to study the paper a little more. And for the ones that are getting impatient, you know, don't worry, this is going to pay off. You know, stay with it. You know, this value then for ρvac emerged, but we skipped over Zakharov, you know, because kind of in the middle of this calculation, we found a direct relationship with the work of Zakharov that was done in 1967.
Yeah.
And Zakharov was a very respected physicist that showed that he could describe little bit heuristically, but very, in a solid argument, a gravitational constant um, based on the modes of oscillation of the vacuum structure.
Yes, exactly. He was describing this gravitational constant as a factor responsible for the elasticity of spacetime, which was directly related to the mode, the vacuum mode we take into account.
So and when he did so,
when he did so,
he ended up using Planck as the cutoff.
Yes, the Planck scale as the cutoff, and this is what we see in equation 221. 220. And so the K is an equivalent of the omega we saw earlier for the modes. And when we solve this equation, we find that the minimal modes is the Planck scale.
Planck scale. Yeah. And so, there's lots of concepts in there as well. There's a concept of coherence and decoherence. This is going to be a really important concept throughout this paper, so I wanted to mention it. And this value that emerged for rho vac, so for quantum vacuum fluctuations, I think we said quantum vacuum fluctuations like some 60 times in the paper. So we like to talk about it in terms of rho vac. So we're going to say rho vac from here on, so we don't bug you with quantum vacuum fluctuations all night long. And so basically, this value is extremely large. This it's a known value. It's been sitting in quantum physics since the emergence of zero-point energy. And it is the value that produced the so-called vacuum catastrophe, that is that, dark energy at the cosmological level doesn't seem to have the same density. In fact, it's 122 orders of magnitude smaller, and so on. And so that created this conflict as well between quantum physics and cosmology. But that's another story. Here we extract the value and we start to treat it in a certain way in which we extend on it, a correlation function. Right?
Yeah, so it was the same correlation function that was presented earlier to extract the zero-point energy, but there we could find when the temperature goes to zero, because we remember that the zero-point energy comes from the vacuum, which can be also modelized with a zero temperature. And what we found is there is a direct, we found in the book that this decoherence processes is directly related to this rho vac, vacuum energy density, and a decoherence time that we called tau in the equation 224.
Yeah, tau in 224.
Yes.
Actually, and 225.
And what was very interesting is that when we took for this tau
Before you get to that,
okay.
Explain a little bit what are correlation functions.
Okay, so the correlation function allows.
Maybe I should go up again.
It's all right. Like,
okay.
Yeah.
Okay.
It's a mathematical tool that allows to evaluate how a wave will interact with a neighbor waves, neighbor either in space or in time, so that you can look at the interferences between waves through this correlation function. So this is why they are mainly used in optics.
In optics, so the interaction of photons?
Yeah, for the interaction of photons.
And lasers, like the coherence of a laser and
yes,
so on?
Exactly.
Yeah.
And here we investigate those correlation functions for the electromagnetic field, which are also responsible for photons, and to investigate how the coherency responsible for the vacuum energy will evolve in space and time.
So to be clear, when the waves are coherent, we have positive constructive interference. So we have a signal, a strong signal.
Yep.
And when they are non-coherent, we have destructive interference, so we see nothing.
Right.
Exactly.
Like it's black.
So now we're seeing, and I want to clarify as well that this is nothing unusual what we're doing. You will find zero-point energy treated with correlation functions in physics books.
Yeah, this part is standard and is well known.
Is well known and standard, and so I want to make sure it's clear we're not doing something strange with zero-point energy. This is commonly used this way. And what's really important there is that all of a sudden you realize when you're using these correlation functions that it doesn't just all cancel out to zero.
Yes, exactly.
It actually is quite constructive. It produces quite amount of energy. And where Cyprien was coming, so now you can continue, is that when we plug in for the characteristic time
of the proton
in these equations,
Or maybe just one point before that to confirm like the destructive interference when we have like a long characteristic time. If we look at the equation 224, we see that if the characteristic time tends to the infinity, the density energy result in being zero, like we see everywhere in space where there is no matter, there is no visible energy density.
And this is coming back to the same graphic that Wheeler was showing, that you know, if you're very far, you don't see it because
like it's flat.
It's flat. It appears flat at very long characteristic time of the system. But as you plug in the characteristic time here of the proton, however, what happens is when you solve the equation is what?
That we find the energy density of the proton, rest mass.
The rest mass of the proton, and it's exact. And we were really surprised when that came out so clean. And you know, the characteristic time we're plugging in is consistent with the proton. It's consistent with the meson's life as well, you know, which is responsible for the force at the protonic level. And so this is just an amazing, like, remarkable result right off the bat.
Yes, and what is very surprising is that by doing such calculation, we can relate the mass energy of the proton to its radius, which is something very, I mean, not obvious at the first
right.
At the first approach. Yeah.
Right.
And by noticing that the charge radius was related to the rest mass of the proton, allowed us to also make a connection between the Compton wavelengths and the charge radius of the proton. And these Compton wavelengths will have a deep meaning in the following section. So yeah, equation 230, we can see that the Compton wavelengths of the proton is equal to a quarter of the charge radius.
Okay, that's all really nice.
Yes.
But we just pulled out the mass of the universe, because the proton makes up the universe, out of
the vacuum. Yes, exactly.
Fluctuations. Yeah. So there's a really big change in the understanding, because in quantum, you know, chromodynamics, typically the bare mass is shielded by the vacuum fluctuations.
It's reduced by.
It's reduced by it. You know, the bare mass turns out to diverge. It's infinite in the standard model, and vacuum fluctuations are utilized to actually shield it so that we actually measure, the rest mass of the proton. In this case, so this is a big change. In this case,
it's a shift in point of view.
It's a very big shift in point of view. In this case, the vacuum fluctuation, coherent behaviors at that characteristic scale produces the mass of the proton. So it's a completely different approach. It's almost 180-degree reverse.
Yes, exactly.
And however, the mechanism of shielding is still present, and we'll see that emerge. So it's not like it was wrong. It's just that what is the bare mass is the question one should ask, right after. So here, another point I want to make, because it's an important point, is that this equation is consistent as well with the Casimir effect. So that is,
yes, exactly.
We can think of it as a coherent state of the correlation function, or we can think of it as two plates or a cavity with the characteristic time of the proton. At that distance, that cavity would experience the energy of the vacuum fluctuation equivalent to the energy of the proton. And those are equivalent.
Yes.
So you can think of it that way as well. You can think of it as when you make a boundary, when you make a cavity, when you make an oscillator, that characteristic time actually defines the energy of that system based on how much of the modes of the vacuum fluctuations are coherent within it. And so that's a concept that's really important for the rest of the paper as well.
Yes, exactly.
Okay. We're taking a lot of time.
Yeah.
Yeah.
Just to summarize these two first parts. The first, we show that ROVAC, the electromagnetic energy density of the vacuum, is essential mathematically for quantum mechanics and quantum field theory, and is visible in in a lot of experimental physical experiments. And now we saw that this very large energy density is mathematically related directly to the rest mass of the proton with a very simple mechanism directly coming from wave interference, like in optics. So electromagnetic wave interference.
Electromagnetic wave interference that relates then the electromagnetic ground state directly to mass. Right? And eventually we'll see to forces. So so then we pass on to a completely different approach. However, it emerged from it, right? So we have the Casimir plates. We have the concept of coherency. We know it gives the right answer. So now let's try to understand what are the mechanics of this thing. Like, let's try to understand how this thing works, right? And so we take that result that we got from the correlation function, and here it's very straightforward, math. All the way through this is all analytical from the beginning of this paper. And so this is very straightforward, and we end up with a cavity in which the characteristic time is of the Planck time with characteristic length of the Planck length and the Planck mass. And so we end up with kind of like a little voxel or a little pixel that in my earlier papers I had called a PSU, a Planck spherical unit.
Exactly.
And so basically, I had got the rest mass of the proton from a geometric approach of the structure of space-time. And, I could get the right answers I just didn't have all the different components and all these since 2012 when I published it,
Yes.
all these time I've like been digging, with the help of Olivier and you to get all that to surface. And so now we kind of find it again. It kind of emerged naturally. Olivier, you want to talk about this a little bit?
Yeah. So we just saw the calculation of the geometry of the PSU to confirm that the Rovac,
The vacuum and
the
density.
energy density vacuum, the vacuum energy density in English.
Yes, in English.
Comes from the packing, the special packing of PSU in space, giving exactly this energy density Rovac. And then we analyze what is the dynamic of this PSU, is mass, is radius, and then we use this PSU to define more precisely what is the quantum structure of spacetime.
So you can think of this PSU as almost like the particles that makes up the vacuum structure, like a Planck, what we call the Planck plasma.
The Planck plasma, yeah.
And
describing spacetime as a fluid.
As a fluid.
Which is not which is not an exotic way of thinking, because when we look at all the cosmological models used, they are modelizing the universe as a fluid.
As a fluid. So you can see on the paper there, we're talking about QGP, which is, the quark gluon plasma. We associate our Planck plasma with the quark gluon plasma at the scale of the proton, at the interior of the proton. We'll see direct relationship later on. But here we kind of start to elucidate starting to describe the nature of space-time at the quantum scale.
So first, we go back to the proton in equation 3.9 and analyze how the energy density of the proton, rho p, is deduced from this vacuum energy density Rovac. So we compute the ratio, and we find an interesting result as being the square of alpha g. And maybe, we need to give a little more detail on alpha g, which is the gravitational coupling constant.
Right. And this, is really important. Like, remember the earlier equation. So now we're looking at the decoherence from Rovac to rho p, right? The energy of the proton. And when we look at this decoherence, we find the square of alpha g. Now, alpha g is the gravitational coupling constant. Historically, it's not actually, it used to be more common in physics paper in the earlier days, when I was a youngster. Now it's less used, it's less known, but it's the coupling constant. It's called that way because it's typically related to the energy of gravity relative to the energy of the strong force, or the energy of confinement. So alpha S is the energy of the strong force. Alpha S is typically given in the order, it's around 1, right, in the order of unity. And alpha G then is 10 to the 40th, 10 to the minus 39, 10 to the minus 40th times smaller. And that is the energy of gravity relative. So gravity is very, very, very weak. And this difference seemed to be directly emerging at the proton scale, this relationship. Well, at the proton scale, you happen to have both. You have the strong force, you have strong confinement, and at the same time, you have very weak gravitation because the mass of the proton is very small.
Yeah.
And so so it's really interesting that that ratio between rho vac and, because we just outputted the mass of the proton from rho vac to the proton level, outputs that constant, and it's to the square. So if it's to the square, it starts to give you a hint that there is 2 times the screening, the reduction of energy. There's 2 times that alpha G occurs to produce the rest mass of the proton from rho vac.
And 2 times a similar reduction as the difference between the confinement force, confining energy, and the rest mass energy.
And the rest mass energy. And so, you know, this eventually, it's leading you to this idea of screening or moments of decoherence, phase transition in the Planck plasma, in the rho vac, in the fundamental, ground state, decohering once and then decohering twice, as it goes through phase transition to eventually the radius of the proton. And since our equations was showing, a relationship to the Compton radius, then the first horizon, of decoherence would occur at the Compton radius of the proton.
Yes, exactly. And this idea of screening shift also the mindset of the decoherence processes, because before we were looking at wave equation, and now we have switched to a fluid made of PSU that we call the Planck plasma fluid. And we now look at the screening process or the decoherence process as a fluid passing through a grid, right? And when a fluid passes through a grid, it lost energy. And we
literally a screening.
Yeah, literally a screening.
Yep.
And we will now investigate the mechanics of the screening, and this is what, and to explain it, we decided to following the early theories of Nassim that he published 10 years ago, to define a screening parameter that we called eta. And eta is defined as
maybe just for the audience, so
yes,
just remembering that the energy density is equivalent to a pressure. So we have strictly this equivalence, and then
yeah,
so
between the energy density and the pressure of the fluid.
Right. I was going to say that, because it's like, yes, it's a decoherence of rho vac, but rho vac
which is
a pressure.
Yes.
Yes. Is equivalent to a pressure. And so the energy density of the system, so you can think of like literally, a fluid that's going through a screening and that loses pressure or density on the other side. And so eta, go ahead.
Yeah, and this eta, the screening parameter, is defined by the elementary particle of the grid, which is the PSU. And a way of describing the screening factor is to calculate the amount of PSU we have on the surface of the first screening surface, which is at the Compton wavelengths. And by defining this eta, we can express the proton rest mass energy density as a reduction in rho vac by this eta lambda. And then we have a second screening parameter defined by eta p, which occur at the second screening surface at the charge radius of the proton.
At the charge radius of the proton. And so here we calculate the actual amount of rho vac energy in the volume, right? And we look at the ratio of this energy or this pressure inside the volume being screened twice, and we recover the rest mass of the proton.
Yes, exactly.
And so now we've started to actually understand the mechanics of this decoherency from the high coherent, you could think of it as like a Bose phase of the Planck plasma in the core of the proton that's decohering twice. Now, I think for the readers, I mean, when you read the paper, you'll get it. But right now, one thing we kind of skipped over a little bit, that surface grid is the number of PSUs on the surface of that membrane. So it is a PSU membrane. It's really important that that's clear in people's heads. So Olivier is pointing at the equation, like clearly the surface of a sphere tiled with PSUs that makes up that filter, that screening that give us the correct masses. And so from there, we want to start to investigate the first screening.
Yes. What does it mean?
What does it mean? Okay, we have this coherent state of the vacuum in the cavity. It has pressure. It's pushing through some kind of horizon. Is there anything in our current physics that would predict that horizon should be there? And sure enough, when you screen ROVAC, once the resulting value, this can be for any surfaces, like meaning in any system in the universe.
Any size.
Now we're generalizing to like any size. It's not just a proton. Well, when you do that first screening of ROVAC, let's say for the center of our galaxy, well, you get the Schwarzschild solution to Einstein field equation. You get a value, a solution that is very well known, and that has to do with the gravitational curvature of spacetime. That is, spacetime curving to produce a very specific, effect, like,
a very strong effect.
a very strong effect.
Stronger than electromagnetism.
Yeah, stronger than electromagnetism.
Confining electromagnetism inside.
Yeah, confining electromagnetism inside.
Yeah, because maybe we should remind that this Schwarzschild solution is the first known solution of the Einstein field equation, which relates the curvature of spacetime to the mass energy.
The mass energy. So this is non-trivial result.
Exactly.
From just a simple screening of ROVAC, at any scale. So the equivalence is really, really important there. It starts to give you, Einstein field equations are thought to be fluid dynamics equations, right? I mean, they
were written like that.
They were written like that.
From Maxwell equation.
Right. And it was the intent that it would be visualized that way. And all of a sudden, you're starting to see there that, like, so basically, when ROVAC becomes coherent, because of angular momentum, because of collective behavior of this Planck plasma, or this quark gluon plasma, if you'd like to think of it that way, when it becomes coherent, it produces curvature. It just like when you pull the plug in your bath, and your rubber ducky starts orbiting, and it starts being attracted to the drain. Einstein field equation describes the surface of the water curving, but here you're getting the understanding that the water itself is made out of little things. So it is smooth at long distances, but it is granular at short distance at the quantum scale, right? Just like the water in your bath is granular at the quantum scale.
Yes.
So this is a really important result. It's very powerful.
And it illustrates beautifully why Rovak is not visible from the exterior, because it's inside the event horizon of the black hole.
Exactly.
Yes. Yeah.
So it is confined by the gravitational field.
Very strongly confined.
Very strongly confined. And in this case, from an energy density, again, that emerged from vacuum fluctuation. So it's saying something as well, very different about a black hole. So theoretically, currently, we think of black holes as the accumulation of mass or energy.
Of protons.
Yeah, inside of protons, right? Inside, a restricted space, so that the energy density gets so high that the gravitational field absorbs the electromagnetic field. But
about the energy density of a black hole, maybe we could remember to the audience that a black hole density could be as low as the density of the atmosphere, of the Earth's atmosphere, or as low as the density of the water, like in active galactic nucleus at the center of galaxies.
Right. Yeah, that's a really important concept as well. It's that the
as
density,
low as rho crit.
As low as rho crit. I was gonna say that's where I was going. As low as the density of our universe, because actually, as we'll see, it obeys the Schwarzschild condition as well. But I think Cyprien, you did the cal for us. I asked you.
Yeah. So when the density of a black hole is very low, it means that the black hole will be very large.
Right.
For example, if we look at the black hole with the density of the atmosphere, the radius will be roughly the size of the solar system, which means that we have matter extending to a very large region of space.
Right. So basically, if we take the air of our environment here, and we put it in the solar system, I think we only went to Jupiter.
Yes, Jupiter. Just before.
Yeah, just before Jupiter.
Yes.
And it was already a black hole.
Yes.
Right. It had the density required to be a black hole. So this and we have to remember that there's a relationship between mass and energy, so that a black hole. So why am I saying all this? Is because this is telling us that a black hole can be the dynamic of the vacuum structure operating at the quantum level, producing this effect without being the result of collision of massive object to eventually make a mass large enough.
Yes.
And that would be very much supported from the latest findings of James Webb's telescope, which is finding very, very large black holes right at the beginning of the universe, which should not be there if it was just aggregation or accretion of mass.
Yes.
So it's changing the view of black holes. And so here we have a surface.
No. Maybe we can go a little bit further.
So the surface
jump.
entropy.
Yeah, let's jump to the Einstein field equation in terms of Planck units.
Right. So from this, from that first screening that gives us Einstein field equation, then we investigate. Okay, well, in the metric of Schwarzschild, whether it's turning or not, the Schwarzschild condition is present whether you're taking the Kerr-Newman metric or and so we look at it and we find, and it's known, but it's not so well popularized, that actually you can write the Einstein's equation in terms of rho vac in the stress energy tensor. On the source side of the equation, you find that rho vac is kind of like the ground state,
the cutoff,
the ground state for Einstein, for the metrical structure of space-time of Einstein field equation.
Yeah, and another interesting observation of this way of presenting Einstein field equation is that the right-hand side term, T mu nu over rho vac, provide an insight about what should be the intensity of the energy in order to curve space-time, at least on the order of the Planck scale. And this energy required to curve space-time is on the order of rho vac, meaning that if we don't have, even at the smallest scale, an extremely large energy, we wouldn't be able to curve space-time and to counter the elasticity of space-time enough in order to curve it and to create an object.
To create an object, that energy will define the object structure that space-time will kind of emerge from, right?
Exactly.
Because it has to have that level of energy to close a bubble.
Yes.
Right.
Yeah.
The quantum foam of Wheeler.
Yeah.
Like a surface tension.
Like a surface tension. A way to represent it, it will be to, when you have a foam film and you want to create a bubble, you have to blow on the film, and if you do not blow enough pressure, the bubble won't form. You have to blow a certain amount of pressure such that the bubble forms, and this equation can be interpreted in that way.
In that way, right.
And it was interpreted in that way by Wheeler when he created the geons.
Exactly, yeah.
The geons,
Geons,
exactly. Yeah. Very good point. And so, now we return to our relationship of the volume surface, so the pressure inside to the surface pressure, if you'd like, and we find this what I call this universal constant that I called phi, and in my earlier papers, and there we discuss a little bit, previous work that was done by others, Zakharov and Zeldovich and others that work on this kind of relationship between space-time and like Einstein field equation and
electromagnetism.
Maybe just one word on the holographic ratio.
Yeah.
It's old, it's not new, so we go fast. But we will see it's a fundamental parameter of the system, which is in fact the scaling of the system. So just to have this idea in mind for the last part.
For the last part
of the discussion.
Yeah, exactly, because it has a direct relationship to alpha G as well. And so we can
now maybe go back to the proton scale, maybe.
Yes.
Yeah, applying the first screening at the proton scale.
Yeah. So so then since we found that screening from examining the proton, and we found Einstein field equation in the middle of the proton, saying, black hole, well, then we look at this mass that we have decohered, right? The energy that we have decohered from rho vac. So we started with the energy of rho vac, very, very high. Now we have decohered to the energy to make the bubble in the elasticity of space-time, basically,
at this scale.
at this scale,
And the proton
right?
scale, yeah.
And so,
And we compound the rest mass energy with this black hole proton energy.
this black hole proton energy, and when we make the comparison, sure enough, alpha G comes out again. Which,
Exactly. We find out exactly alpha G.
Exactly alpha G that like has again this relationship. So remember, we're talking about densities, which are equivalent to pressures, and these densities are dropping across horizons, across, filters, or if you'd like, and the alpha G is a representation of the energy, the force on one side of the horizon, on the coherence, on a certain coherent level of the horizon that we call the black hole, and on the other side, right, the decoherence that occurs between that horizon and the next. And so that's really remarkable that just comes out this way. I had found it in 2012. But I didn't have all the mechanism to be able to explain exactly how it occurred. I knew clearly it must give a relationship between gravity and the strong force, the rest mass, and the black hole mass. The mechanism was not complete at the time. We'll see that it completes in this paper. So, I think here we do a little bit of a discussion because clearly we understand that it's jarring to think of
a black hole of the size of the proton.
Of a black hole the size of the proton being constituted of a black hole. It can be jarring.
Could be strange.
It could be strange. However, you have to keep in mind that the standard view already has a bare mass that has, infinite, divergence in it in terms of energy. So, it's very much similar to what we found. And that because of that, many people before us have, presupposed or discussed the possibility,
came to the conclusion of, although Einstein really didn't have all this quantum mechanics to back it up, but between him and Rosen, so here maybe you can show that slide.
Yes.
Where we have like some of the quotes of Rosen's, Einstein and Rosen in his paper. You want to read it?
Yeah, so Einstein and Rosen were very much intrigued by the fact that there were some divergence in Einstein field equations, and they tried to model a particle from a pure geometrical point of view. And they realized that the particle were made of bridges that connect to part of space-time. And they were describing the many particle system can be represented by a regular solution of the field equation, and they correspond to a space of two identical sheets joined by many bridges. And another theory that were based also on this concept of black hole particles was the concept of Wheeler that we talked earlier with the quantum form. And here we put another citation from Wheeler. So we are therefore led to consider the view that the electron is nothing but a collective state of excitation of the foam-like medium, and this collective disturbance is suggested by the slightly closer spacing of the wormholes. So at that time he was talking about wormholes, and then later he called them black holes, and he was the first to name them like that. And more recently, we have also another Nobel Prize, Susskind, who wrote.
Susskind is not Nobel Prize.
Sorry.
But it's interesting because he's coming from string theory, which is another field of physics.
Okay, sorry, I thought he was Nobel Prize.
Yeah.
And interestingly, he wrote that one of the deepest lessons we have learned over the past decade is that there is no fundamental difference between elementary particle and black hole, meaning that from the equation of physics, there are no reason why particles shouldn't be black holes.
Exactly. And I think you skipped a little bit over some of the quotes from that we've added now. We're gonna have a revision because I just wanted to put that other quote in there. From Einstein and Rosen, clearly, considering the possibility that a particle is literally, the intersection point between two sheets of space-time producing a wormhole, and it's such a close description of this Casimir cavity oscillator, and this idea as well, because now we have theories that came from Nassim and Susskind talking about ER equals EPR, which is ER is Einstein-Rosen,
wormholes,
and EPR is Einstein-Podolsky-Rosen, which is
quantum entanglement.
Quantum entanglement, describing basically that they're equal. That is that entanglement at the quantum scale is actually because there's micro wormholes that are connecting particles everywhere. And it's kind of, there's that great story of Wheeler calling Feynman in the middle of the night and saying, I figured it all out. There's just one electron and it's wormholing all over the place. And we just think there's a bunch, but there's only one. And so, and Feynman telling him to go back to bed. But basically, this concept keeps re-emerging, and in many other cases that we're not citing here because they're not prominent people in history, but certainly from prominent people in history, the concept that black holes physics is involved at the quantum level, because of the energy of the quantum level curving space-time at high energy levels, is not foreign at all. Okay, so now that we've said that, we can continue. So
we have the first screening applied also at the Planck scale and defining the kernel 64, which is well illustrated just at our right.
Yes.
In the room with this piece of art.
Yeah.
Representing like a 64.
And I don't know if people can see it, but it's right there. In any case, this actually is interesting because it kind of emerged naturally from the physics I was elucidating a very long time ago, some 30 years ago, and it emerged naturally in this geometric exploration of the structure of space-time I was doing, and I published it in earlier papers. But this here, we just wanted to pull it out again to clarify, because it wasn't clear in the earlier paper. But basically, when you consider the Schwarzschild solution and you put the Planck mass in it, you get the Planck length with a factor of 2. So there's actually no reason that would be true, either if rho vac is in the source term of Einstein field equation. So it comes out that way because rho vac is involved,
Yeah.
and that little factor of 2 has meaning because it gives 2 Planck's lengths, right?
Yes.
So Einstein field equation defines really the first black hole kernel of rho vac from the PSU, from the Planck spherical unit, as the first black hole being 2 Planck lengths in
Yes.
diameter.
Yeah.
And when you apply the holographic mass solution, so the geometric solution to Einstein field equation, to figure out the geometry of the thing, when you apply then the volume vacuum fluctuation over the screening, you get that there is 64 PSU oscillator in the volume and 64 on the surface. And now you have a first screening because that gives 1 multiplied by the Planck mass gives you the Planck mass. So it's the first screening. It's not an addition. It's not a summation of all the little Planck spherical units. Otherwise, it would be 64 times the Planck mass. It's the Planck mass, so it has reduced. It's the first black hole, so we called it.
It's the smallest black hole.
It's the smallest black hole, so we called it the 64 kernel, or the kernel 64 in our paper. And why are we going through this is because it has meaning, it has importance in the mechanics of the screening. And so you can see now that the screening from the first screening at the Compton radius to the second screening at the charge radius, the holes of the mesh has got bigger, and basically because now you've created more decoherency in the rho vac, so it's made you can
aggregates,
islands, and so the energy drops, and now the next screening is a little less intense. Right?
Yes, exactly. It was as if the second grid has different mesh, and when we compute this new mesh of the kernel 64 into the screening parameter, meaning that we now evaluate the amount of kernel 64 we have on the proton surface at the charge radius surface, we find the second screening parameters, such that the equation that we found earlier can now be reduced with the energy density of the proton rest mass is rho vac divided by the first screening parameter and the second screening parameter.
Exactly. And this image kind of blows a little bit the cover on the pressures that we are calculating or that we are getting from this change in density having relationship to the forces. But I'm going to skip over because we'll get into the forces very soon.
Yeah.
Since we have to finish this very soon.
Yes.
So maybe we already explained that this is the second screening applied to the proton mass with the first and second screening.
Right.
This is the energy density of the proton that we already saw. And now we are exploring the Hawking radiation, meaning like the electromagnetic radiation emitted by the black hole.
Exactly.
And we applied this electromagnetic radiation, this black body radiation from the black to the black hole proton.
Right. So we're looking at, so if we have a black hole at the core of the proton, right, we have rho vac in the middle, we have a black hole proton. Then if Hawking radiation is correct, then we should be able to calculate the amount of energy that this little black
radiated
hole
by the black hole,
radiated by the black hole, or the temperature, the surface temperature
Yeah.
of this black hole.
Because what demonstrated Hawking was more like a prediction relating the mass or the entropy of the black hole to its temperature, meaning that if a black hole have a temperature, it should radiate like a black body, like we saw earlier with the Max Planck theoretical development. And this is why in the radiative part of the proton black hole, we use the Stefan Boltzmann law.
Exactly.
And we could remember the analogy between the surface temperature of the black hole and the surface gravity, because there is an equivalence in the vacuum between the temperature and the acceleration. And the surface gravity is the acceleration at the horizon of the black hole.
Right. I mean, we could get into, you know, Unruh effects and so on
Which
as
is
well.
the Unruh effect.
Yeah. But here, if you can just describe this equation. So that
we look at this equation. So it's the Stefan Boltzmann law that we saw at the first beginning of the paper. So related to the surface temperature of the black hole, we have the horizon of the black hole, from which the electromagnetic radiation is emitted, and then the last term is the characteristic time or the coherence time of the proton, the same as we used before. And when we compute this energy, we find with the black hole temperature of the black hole proton, we skip.
I just want to mention here.
Oh, you want to detail the entropy?
Just a little bit, the entropy. It's important to understand as well that when Hawking did this calculation, he did it in like orders of magnitude, kind of first approximation. He didn't consider the geometry so much. He used the Bekenstein, you know, conjecture.
And he used analogy to find that it was similar to a temperature.
Similar to a temperature, exactly. So it's an analogy. It was a little bit with the hands, and in our case, we're not using a black hole in the universe that you can't go and measure the temperature. We're actually measuring, like we're using a black hole that's inside the proton, where we have a lot of data, right, about you know, the pressures involved and its energy. And so in our case, we have to make sure the geometry is correct. So Hawking did you know, script L square for the entropy of the surface, meaning he was piling squares of Plancks. The universe is not making squares, and certainly from our equations we see that they're spherical units. So we change the squares to spheres. This is why we
introduced the coefficient C, which is the surface capacity.
And then the spheres can only pack with a certain capacity. So we did close packing of spheres, and we calculated the capacity. And when we did all that, which is completely appropriate geometrically, we got the mass of the proton. So the rest mass of the protons, meaning that our little horizon of the little black hole is letting through, in Hawking radiation, through that screening, the energy that we call the rest mass, the proton, and the pressure, which we'll see in later calculations. So that's like already, that's remarkable. Okay. Now there's an argument that comes along, that is that Hawking radiation predicts evaporation. That is, the proton should evaporate because it's radiating some energy. And it's important as well to remember that Hawking radiation is very much linked to vacuum fluctuations. The mechanism is described as the virtual photons emerging near the horizon of a black hole. One falls in, one is emitted, and that eventually, evaporates the black hole. And so we calculated that evaporation. However, in our case, again, that source term for the oscillator has to be considered. You can't just take the energy of the black hole, because the source term is rho vac, is the energy of the vacuum fluctuation inside the system, not just the outside, right?
Yeah, actually, it's at the root of the black hole, so
exactly.
the system
So
can still furnish energy while the proton is evaporating.
Is evaporating, yeah.
And you mean the 0-point energy we were talking about in the first part?
In the first
For
part.
the oscillator with the dissipator.
So a black hole the size of a proton would from recent car, for instance, would
Explode.
approximately be done with evaporation in our epoch of the universe. It would have radiated all its energy.
Yes.
But that's assuming that the source that made the black hole is no longer there.
Yes.
And so in our case, our physics clearly demonstrate that the source is actually the source of the black hole itself. And so when you calculate with rho vac the amount of time it would take the black hole to evaporate, we get 10 to the 44 years.
Which must be compared with the age estimate of our universe, which is 13 billion years at the moment.
Right.
So it's very extremely long compared to the age of our universe.
Yeah, it's how many billion years? It's 10 to the 35th
billion years. It's 35
years.
Yeah.
To the 35 billion years.
Which is barely infinite amount of time.
Right, it's almost an infinite amount of time.
And the way, yes, to better understand this time, we reverse the equation and trying to understand and to calculate what would be the reduction of the proton size over the age estimate of our universe.
How much waistline it would have lost.
Exactly.
over the time since the beginning of, since
the 13 billion years.
13 billion years. Yeah.
And what we found is that it would have reduced 10 to minus 52 meter, which is infinitely small compared to the Planck length, meaning that we cannot observe such reduction, and it's almost zero.
There would be no evidence of any decay. It would be very, very, very stable. This is a value that's below the Planck length. It would have lost less than a Planck length over that time.
Yes.
So this is very clear that both the Hawking radiation principle is present, right? Because it does give the correct mass for the proton, and that mechanism is stable over very significant amount of time. Now we passed a little graphic on the way down. That graphic is in the wrong place. We have an updated version. It belongs to that next section that has to do with the with the radius, the proton. And we gotta move forward. So in this section, we actually review a little bit of the fact that this approach that I had published in 2012, sent to the Library of Congress in 2012, that value that I got for the radius of the proton is now the standard value of co-data
for the charge radius of the proton.
For the charge radius of the proton, and that co-data value was the result of multiple experiments since 2012, and that it was basically implemented to co-data in 2018, right?
Yes.
Yeah.
And when it was implemented to co-data, was predicted by the holographic mass solution is 4% smaller than the standard model value. When it was implemented to CODATA, basically the standard model had to do adjustments.
Stretching.
Stretching, adjustments, patching, so that it continued to work because the radius of proton is such a fundamental value in quantum mechanics. And this graph that's a little bit in the wrong place currently, is the graph that shows the relationship of the proton radius to all the other branches of quantum mechanics. So this important prediction, it's the kind of prediction that tells you that you're on the right track and you're finding the right mechanism. And in our case, it's completely consistent. That is, the radius and the mass are completely consistent to produce the correct values.
Yeah,
Okay.
and another way to reinforce this correct mechanism is to look at the forces that we can extract from this first calculation of the energy density within the proton structure.
Exactly. And we're kind of gonna have to skip a lot, but let's try to. Okay, so here
We can go from the pressure and computing the force from the pressure.
Yes, exactly.
Right.
So a way to evaluate a force. So we have described two different mechanisms from the beginning. The first mechanism was the decoherence process from the vacuum fluctuation, highly coherent vacuum fluctuation, to the rest mass of the proton. Then we define the Planck plasma flow as a highly coherent mode of the vacuum, and then we define the screening mechanism as if the Planck plasma flow would go through grids, and by going through the grids, it will lose energy, and it will result in the decrease of pressure. And the way to relate the energy density to the pressure is through an equation of states, like equation 4.8. That is generally used in the fluid model for the universe to describe our universe.
Right.
And we decided to use the same type of model here. And then we evaluate this pressure force applied on the PSU cross-section to evaluate what is the force experienced by PSU within the Planck plasma flow.
Right.
And
so what is the force they're feeling inside there?
Exactly. And interestingly, we found the Planck force as a ground state force for the Planck plasma flow at the core of the proton.
Exactly. So what we found is, that this model can describe, it gives the correct answer for the Planck force at the Planck level in the Rovac.
In the core of the proton.
In the Rovac state, right? And we related against to Einstein field equations, right, where we show that yes, you can actually show that the stress energy tensor, which is on the right side of the metric, can be written just as it can be written with Rovac, it can be written with the Planck force, making the Planck force kind of like the ground state force for the gravitational component, which is the curvature of space on the other side of the equation over there. So we're gonna skip because we gotta move forward. But basically,
we already talked about that. It's the analogy with the surface tension.
Surface tension.
It's the analogy with the surface tension. So
now we will look at the first screening of the force.
Right.
So going from the Planck force to the next force.
Yeah. So similarly to vacuum energy density reduction, we investigate the reduction of the Planck force into different forces following the exactly same mechanism. And after the first screening of the energy density, we found that the pressure force experienced by PSU in the Planck plasma flow is
after the first screening.
After the first screening.
So at the horizon of the first screening.
So at the Compton wavelengths surface
after the horizon.
After the horizon,
yeah. Will be 10 to the 4 Newton, around 10 to the 4 Newton.
Go ahead.
Which correspond to the strong force.
The color force. The color force.
Yes.
Which is a value that's really interesting because it's a value that is now being measured in the quark gluon plasma.
In the accelerator.
In the accelerators. So it is a measured value. And we kind of like land on it just like that.
Yes.
It's remarkable. I think we give
it's more an estimate for the quark gluon plasma force.
Yeah.
Because it's difficult when they are trying to analyze the result of the particle collision in the accelerator. They don't get like straight measurements. So it's kind of an extrapolation of the amplitude of the force, but we are straight in the range of what they estimate.
Well, we had 4.54, and the measurement or the interpretation of the measurement is at 4.43. But remember, we just screened from the Planck force, which is at 10 to the 44, Newton.
Yeah.
And so
it's 40 orders of magnitude away.
Yeah, 40 orders of magnitude away. So it's remarkable.
And so we, after the first screening, we look at the second screening, and we get another very interesting result, because it corresponds to the energy density of the proton, but this energy density, when interpreted in terms of pressure, it corresponds exactly to the pressure, to the interior pressure of the proton, as they measured like recently and published in Nature.
Yes, this was measured very recently. This 10 to 34 Pascal, which correspond to the pressure inside the
proton.
Yeah.
So this is really a remarkable result again. And I'm thinking that it cannot be a coincidence. And this is I'm sorry, I got a little bit disturbed, but basically it really is important to be clear that we're applying the same mechanism as we applied for mass. And we're finding the right pressures or the right forces, that
are currently measured in accelerators.
Exactly.
And in laboratories.
In laboratory. So.
And this second and this force resulting from the second screening correspond to the weak gravitational force, which is estimated at the nuclear scale.
Right.
And the one that makes the gravity so weak at the quantum scale.
Right. So, and I think it's important to mention that this force that we find at these scales are present, meaning in the standard model with a different mechanism that is, QED, and that has a lot of complexity, and that doesn't have an analytical solution that is, very, very complex, that has a lot of free parameters in it, and so on. And so in this case, it's very, very straightforward and very analytical. It's analytical, and it outputs the correct value, which is actually quite remarkable. And so we've recovered. And as well, it's important to realize that like the color force is the idea that like two quarks would like inside the proton, if you tried to pull them, what would be the force where the gluon tubes that is
Before the gluon tube snaps.
yeah, before the gluon tube snaps. Do we see you in there, Olivier?
We are looking just at the paper.
Oh yeah, okay. So I just want to say, you know, this is like a really remarkable result. However, we weren't satisfied with it fully because it's like points along the way, of the
It's just value of the force at the horizon.
at the horizon.
We wanted to have the details and the evolution of the force in the volume.
All right.
In order to make this continuous solution between the different horizon, we look a little bit deeper at the Einstein field equation,
Right.
and especially at the Kruskal-Szekeres metric.
Exactly. So basically what we wanted to know is, okay, you know, we have these points where we're getting the correct force based on measurements, the correct forces, because it's the color force and, you know, the strong force, that is the force outside the horizon of the proton that makes the protons stick together in the nuclei. But what is the profile of the change from the color force, which is like 4,000 Newton, to like the residual force, which is much weaker, right? So what is the profile? And so we looked at Einstein field equation to give us this profile. And we looked at it in terms of the KS matrix. And so the KS matrix, you want to explain it a little bit?
Yeah, so we've talked earlier about the Schwarzschild solution of the Einstein field equation. And in the Schwarzschild solution, we have two singularities that appears in the metric. One at the center of the black hole, and one at the Schwarzschild radius. But the Schwarzschild radius is not a real singularity, meaning that if a particle fall into the black hole, you won't see the singularity at the black hole horizon.
Yeah,
at the radius Schwarzschild.
The horizon is just a mathematical singularity.
Exactly.
Right.
And by using the Kruskal-Szekeres coordinate, you can avoid this mathematical singularity at the horizon. And what is interesting is that this coordinate integrates how a particle would fall into a black hole. And when we look at this metric, equation 4.25, yes, I know that the screen is a little bit small, but in this coordinate, we can see that we have Yukawa potential, meaning that we have an exponential, a decreasing exponential, which could be responsible for the very important energy drop or pressure drop throughout the different surfaces.
Exactly. So basically, in Einstein field equation, when you take the proper coordinates of the system of the test particle that's crossing the horizon, you find this Yukawa type potential that emerge.
Yes.
And as well, you know, so we start to look at that because it's commonly related this Yukawa potential to the strong force interaction or the range of the strong force.
Exactly.
Yeah.
So we created this. I mean, we built a general gravitational potential.
But before we went to that, I wanted Olivier to talk a little bit as well about the Einstein Klein-Gordon equation, which we mentioned in there as well. So we didn't have time to give all this in this paper. This will be part of a upcoming paper, but you want to talk a little bit about the Einstein Klein-Gordon equations as well?
Yeah, because our idea was to incorporate general relativity and to find out how general relativity could be expressed at the proton scale. And like Cyprien said, the Churchill solution is a first interesting approximation, and because it gives it gives a solution of Einstein field equation at the exterior of the horizon, and where there is no matter, and where there is matter energy, we need to switch equation, switch solution, switch metric. And an interesting equation is the Klein-Gordon Einstein equation.
Right.
Meaning that in this equation that is used in cosmology, the stress energy tensor is replaced by a Klein-Gordon equation of a scalar field representing the wave interaction in the space.
In the space.
Which was corresponding nearly perfectly of what we were describing at the proton scale with the quantum vacuum fluctuations.
With the quantum vacuum fluctuations. So that will appear in further publication because it was too much to treat in this one. But basically, all this gives you the idea of what we had to use. It gives us all what we needed to use to be able to write an equation of the energy potential so that we would have, a description.
A continuous description of the force at the proton scale.
At the proton scale.
And more precisely, we deduce a gravitational potential.
Exactly.
A gravitational potential energy at this scale.
At this scale. So let's share the paper again.
We were looking at the gravitational energy potential, so it's equation 4.28. And we were saying that we can deduce this directly from Einstein field equation when considering the stress energy tensor as a Klein-Gordon equation.
As a Klein-Gordon, and from and this Yukawa type of potential from the Ks metric or the Ks coordinates of a metric where we take the proper coordinates of the particle approaching the black hole. And this Yukawa type potential emerged. And from this, we were able to build, a potential so that we could see the profile of the force after the
two screening.
The
the first and the second screening.
Exactly. So
and giving an analytical expression for the forces, for the strong force.
And giving an analytical solution to the strong force. And so we build the potential. And so it looks like this equation 4.28. So you want to describe it a little bit, Olivier?
Yeah, so this equation contains three terms. The first term with alpha g, so alpha g and alpha s are the coupling constant. Alpha g is the gravitational coupling constant, and alpha s are the scaling of the force at the nuclear scale. So this potential is valid at the nuclear scale, and it's expressing the force at the nuclear scale.
Right.
Inside and outside the proton.
Inside and outside the proton. And so these terms then work in such a way that you know, as the scale grows, so that as we grow through the scale, the potential of R, the terms become a term that's very, very strong at short distances, become
Disappear.
negligible at a larger distance, and then that again becomes negligible at a higher at a larger distance.
Yeah,
again.
you can recognize what we called in physics a skin effect, with the length characteristic of the first screening being the Planck length, and the characteristic length of the second screening being the Compton radius of the proton.
Right.
And then from this gravitational potential, we can compute by doing the gradient of the potential, we can compute the force, the expression of the force.
Right. And so then we computed that to see if we recover the correct values, if our potential is correct, and you know, trying to tie into any measured values, right?
Yeah.
Which is not obvious.
And the previous values that we already computed with the screening mechanism.
Exactly. And so basically,
and
an equilibrium between this strong interaction, what we call generally in physics residual strong force, and the electromagnetic repulsion. And by looking at this equilibrium, we found a value of 48 Newton, which is the characteristic intensity of the force.
Yeah, that is being measured. Yeah. So so now, you know, we've gone far from the proton, and we're seeing that the profile of the force is correct. And I want to mention as well that like this so it's nailing all the forces along the way, but that characteristic value at which the force drops to what is in the range of what we measure in the nuclei of proton, that's keeping the protons together, is that length of 2.6 is what you find in the latest experiments published in Nature and so on, you know, which is the distance that you find in the nuclei of protons.
Exactly, it's the typical distance that we can measure in, for example, alpha clustering, which correspond to the size of the helium atom, and so it's.
So we're nailing that one too, and we're nailing it at the right distance.
Exactly.
And so that's really remarkable. It's very powerful, and you know, that's why Olivier went to that graph. If we can zoom it a little bit, and where you see basically what's happening with the force, where you see that the force drops dramatically from the Planck force very, very sharply. The first screening, remember, the first screening has much denser you know, pixelation, and then it's almost stable across the whole interior part of the proton. It's almost constant, which is another value that is estimated by the standard model, that the force would be almost constant for the duration. And then at the horizon,
because in their representation, the interior force between the quarks inside the proton is given by the strength of the gluon tubes.
In their case, yeah, it's constant, but and then eventually it drops again fairly sharply
from the second
screening, to eventually reach a Newtonian type gravity force, right? A 1/r type of range, you know, gravity at the end. So So we've unified.
And basically, we added general relativity at the quantum scale.
Right.
Yeah.
We added general relativity at the quantum scale with ρ-vac, with the quantum vacuum, electromagnetic quantum vacuum fluctuation, and the mix of the two gives us the masses and the forces that we measure and that we experience at the quantum scale. This is a very powerful, fundamental discovery. And it is analytical. It is beautiful. I'm very, very proud of you guys for helping me do this and nail this. And you know, it's been you know, I'm still integrating those results. So it has large impact in many different spheres of physics and technology, and we can discuss that a little bit as well. But you know, when we then you know, look at this potential here in terms of
binding energy,
the binding energy,
the nuclear energy, binding energy of the atoms.
At, you know, following our potential, we, you know, here we find that at a radius of 1.3, which is approximately the measurements they're doing, right, for that binding energy as well, we find the correct, you know, we're inside the envelope of what they're finding in the experiments.
Yeah, for the binding energy.
For the binding energy. So it's all coherent. And basically now we've kind of like gone through all the possible measurements that we have today, you know, describing the forces that are being experimented on at the nucleon level.
Yes, exactly, yeah.
Yeah. So, so we have a little graph describing this, but we're going to skip over that. And so here we finish with the discussion. And in this discussion, we wanted to say, okay, so if this is valid at the proton level, and we've used Einstein field equations, what happens if we, you know, we applied Einstein field equations at the quantum level? Okay, so what if we apply, you know, ρ-vac at the universal level?
Same mechanism.
Yeah, the same mechanism. Do we get something valid? Do we get something even in you know, we would have been a few orders of magnitude, I would have said, wow, you know, that's really good, because we're gone from a proton to the universe with the same mechanism. But it's better than that. It's actually very good.
It's exact.
It's exact. You know, if you apply the same mechanism, so you take ρ-vac, you screen it with the surface of the horizon of the universe, for the observable universe, you get this value, which is the value of ρ-crip. ρ-crip here,
critical density of the universe,
which is the critical density of the universe, or the critical pressure of the universe, if you'd like. And this is the critical pressure or density, which includes dark matter and dark energy. That is, it's all of the mass required for the universe to look the way it looks, without having to add any fudge factors, any exotic
any dark energy,
or dark matter or exotic particle or anything like that. You know, it just gives you the straight up answer for the mass of the universe. And I mean, we had to put it in because it's just such a remarkable result. Of course, there's so much more that has to be done in cosmology, and we've done a lot that just we couldn't put in this. The paper was already so long, And this talk has been a little long. I'm very sorry about that.
So basically, we found again that the universe is a black hole. Respond to the condition of a black hole.
Yeah, correspond to
Corresponds.
the condition of a black hole. And you know, we're not the first ones to have noticed this.
It was published in Nature in 1972.
In 1972, it was published in Nature that the universe may be a black hole. Again, you know, it might be a little jerking to like think of it that way at first, just like for the proton. But you know, here you have Carr and Rees that published in Nature scaling law. You know, showing the universe as on the black hole line, this reproduction of their scaling law, and showing that objects tend towards black hole density. Interestingly, in the middle, what year was this published? I can't remember.
72.
72, yeah.
79.
79,
yes.
79,
yeah. Here you have the exploding hole, which corresponds to the black hole proton that Rees and Carr had put on their scaling law, and they thought of it as a primordial black hole that would have approximately exploded or evaporated at this time, and so they put it in there. In our case, we've shown that it wouldn't have evaporated at our time, not anywhere close to our time, because it emerged from Rovac as a source. And so we thought it was interesting and actually very appropriate to cite this seminal paper, really.
Yeah, it's really interesting because it provides what we call a scaling law, meaning that how can we relate the structure of very small object to the very large scales.
Exactly.
And it also justifies the fact that we put so much energy in understanding the structure of the proton, because we know that once we have this structure about the proton, we can scale it to the universe and to larger objects such as galaxies, planets, solar systems,
multiverses,
and find the correspondence between this tiny structure to the very large scale.
Yeah, and it's important as well to notice that in this scaling law, the scaling factor, was that what you were going to say?
No, I was jumping to the next part.
You were jumping to the next one. I was going to say that the scaling factor that Rees and Carr identified that scales all these things in the universe is alpha G.
Yeah.
So
the strength of the strong force that now we know it's a gravitational force.
That is a gravitational force, or the Planck force being the gravitational source of all forces.
Mm-hmm.
So we've continued on this exploration a little bit in the discussion, because in the discussion we felt free to like extrapolate a little bit, and so we extrapolated a little bit, and I did this calculation a while ago, and I thought it was kind of really interesting. It says something profound. We don't extrapolate on it in this paper, but the fact is that if you actually take the quantum vacuum fluctuations
inside the proton,
inside the volume of a proton, that you remember we screened twice to get the rest mass, when you calculate that the energy that's in there, you get the energy of Rovac for the universe, right?
You get the energy of the universe.
You get the energy of the universe.
You get the mass of the universe with dark energy and dark matter.
And dark matter inside the proton. And so you get this feeling of just like Wheeler's wormhole particles, that the whole thing is connected, that the whole thing is entangled, and that the volumes are actually shared across, like a network where the black holes, like the core of the proton, is the hub of a network of wormholes that connects the whole thing together, and so that you have a shared value of energy.
And you have a perfect illustration of the holographic principle, meaning that every piece of the universe contains all the information of the whole universe.
Of the whole universe. And you know, that's really kind of something that's been in the folklore of philosophical thoughts for many, many years and eons. And you know, it's remarkable to see it just emerge like that, because it's mathematically very accurate and powerful.
Yeah, but keep in mind that even if you think that you have all the universe, all the information of the universe in every proton, this information is screened twice.
Yes.
Thus, it's very difficult to access it.
It's a whole other story to access it, right? And on that subject of the screening, the next calculation we put in is thus that the other remarkable thing is that if you calculate all the little Plancks, you know, on the surface of the proton, and then you sum up for all the protons in the universe, so all the surfaces, all the surface screening of the proton in the universe on equation 5.5, here you find so the n proton multiplied by the screening of the proton is actually, you know, it's approximate, because the number of protons in the universe is another thing, but it approximately equal to the surface of the universe. Very, very close. You get a pi, or, you know, one kind of, you know, in the order of unity, the relationship. So the screening of the universe is equivalent to the screening of all the protons inside the universe, in which the inside of these protons has the energy of all of the universe. So it's a remarkable universe, and that's why. Yeah.
But in terms of pressure, it makes sense. In terms of fluid dynamics.
In terms of fluid dynamics, in terms of pressure, it makes sense, so that the system is stable.
Yeah.
So that the system, like the soap bubble, can stay, you know, under this enormous external pressure, is matched by this internal energy. And so that's the end of the discussion in our paper. A sense of scaling. Again, we've worked out much of this scaling in a much more detailed way, and we've worked out some of the formalism that has to do with temperature, thermodynamics, that has to do with frame dragging, fluid dynamics of the Planck plasma, and all this, and that will emerge in further papers that will be published soon. So stay tuned for those. Okay, so now we've taken a long time, almost an hour more than what we were supposed to take. We were interrupted for a little while. Took us a little while to recover, but I would love to take some questions. If there's still people out there listening, I would love to take some questions, and you know, we can discuss a little bit some of the things. I really, really appreciate you guys sticking around for this, and I'm really excited to share this with you guys. It's really been a long journey in my life, and I'm really excited as well, and glad to be able to collaborate with such amazing, you know, collaborators, and we wanna collaborate with more people out there. So please help us spread the word, and we're open to any criticism,
are
comments, so on.
There are some good questions.
Oh, yes.
Yeah.
So we're gonna take the first question
Okay.
that have raised many attention in the audience. Do you or ISF have an idea or concrete plan to extract energy from the zero-point energy field?
How did I know that that was going to be the first question? It was the first one yesterday in French as well.
It was also the first
Yes.
question, yeah.
Yeah.
So people are very curious how to extract this energy, and do we have any plan?
Too.
Yeah.
Yes. Well, of course, this is a completely new way to look at energy.
Mm-hmm.
It's a completely new way to look at gravity. And in both case, energy, mass, gravity on the other side, in this new way, you end up in the same place, which is quantum vacuum fluctuations. And these are electromagnetic fluctuations. And we know how to control electromagnetic field in very accurate ways. And so it becomes pretty well a roadmap to how to extract the energy from vacuum fluctuation, how to interact with the vacuum fluctuation.
Basically, the question is how to interact with a black hole. Because now we understood really what is a black hole. And we already have, and it's nearly half a century old, we already have all the knowledge, the theory on how to extract energy from a black hole.
Right.
This was already known.
Right. From
Zeldovich. And even now recently published in Nature with a world protocol on how to extract energy from an acoustic analog of a black hole.
An acoustic analog of a black hole.
And now we have the key, the understanding of the true nature of a black hole and how we could reproduce a black hole at a laboratory scale.
Exactly. And basically, remember, we're dealing with oscillators.
Mm-hmm.
So I would just throw this out there, just out there, that most likely, resonance, coupling have something to do with our capacity to interact with the energy available at the atomic scale of systems. And it leads, but this is much more, already being able to extract energy from vacuum fluctuation will have a huge impact on humanity. But it's even more exciting for me to see that there's a direct path from there to gravity control. That is, by understanding how to deal with these pressures, we can create pressures in regions that we control to produce gravitational fields that could be directed and so on. And it would lead to incredible advancements in space exploration, in our capacity to extend our civilization past this planet and so on, by controlling gravity with electromagnetic fields. So this is really powerful.
Okay, maybe we should take a second question.
Question, one that will be interesting for you. How can we represent in a new way what the speed of light represents? Perhaps the viscosity of the Planck plasma?
Oh, very nice.
This is funny because the equation was on the window of the laboratory in the US.
Exactly. We actually came to that same conclusion. Very good. Who wrote this?
It's Brad McDoway.
Awesome. Good job, Brad. Good thinking. Amazing. Yes, we actually found in our exploration that we will publish soon, of this Planck plasma dynamics. So circulation of this Planck plasma dynamics, we were able to extract the dynamics of that Planck plasma including its surface tension and
Its viscosity.
And when we calculated all this together, we ended up with the speed of light, out of the equation. It's a little bit convoluted the way I'm saying it, but it's something like that. And basically, you're correct. Like, the speed of light is the speed of light because of its interaction. Like the movement of photons in the universe is tied into the, you could think, like, wavefront dynamics of this Planck plasma. Would you describe it like that?
Yeah, exactly. And it's very nice because it was coming directly from the analogy between space-time and fluid dynamics.
Yeah, exactly. And analytically, meaning coming straight out of space-time. Yeah, it actually took us by surprise. It was remarkable. So many, I keep saying the word remarkable. I'm not doing it on purpose. I'm just amazed myself. I in the acknowledgement, we added that we acknowledge, we wanted to thank the universe for its, great mathematical beauty.
It's inspiring mathematical and physical beauty.
As well, we omitted, and that will be in the revision, to thank all the people at ISF and Taurus Tech and all this that have supported us throughout the years. That includes all the people you see on our website. I just want to, it's just so beautiful. And it's so, it just fell together, just such like beautiful pieces of the puzzle. And you see, people are becoming aware of the information just like that. Brad just jumped to like, oh, because it, like, when the pieces of the puzzle come together, all of a sudden you can see, like, the implication in physics at many different levels.
Yeah.
And I'm just so excited to see what's going to come back to us.
And literally, creating all this link between these different parts of physics, you are unifying physics.
Right, exactly.
Just putting all these pieces together.
Yeah,
like a big puzzle.
People ask me, in the last few years, they're like, wow, I can't wait to see your publication and all this. I commonly tell them, I didn't find anything. I just put the pieces together in a different way. And really, all the pieces were there.
Yeah.
Right? And so it's kind of remarkable. It's just that pieces were found in different time in history. And so, and with different formalism that didn't clearly connect. So it was hard to, for instance, associate a black body radiation to a black hole that was like found in the 90s, right? Where black body radiation, was from the beginning of the century. So it really was just a question of putting things in a different order.
Okay, maybe we can take another question of Jeffrey, who is asking, excited to know the solution of the greatest mystery of why the fine structure constant alpha is what it is, 1/137,
Right.
in our unified science. So maybe the question is, okay, what is the place of the alpha in the context of the unified science?
Right. Well, we found the place of alpha in unified science, and it is much more mechanical than previously believed, and maybe for some not as exciting as some, some esoteric idea about alpha coming from the Word of God or something. But it will appear in papers that are coming up. So I don't want to. I would have to give you too much context to be able to explain.
But maybe we can share the fact that it will have to deal with refining the scaling law that we addressed in the discussion, meaning that we have the scaling law following the Schwarzschild solution, the black hole solution, which is more vertical description of the scaling, and the alpha will be involved in more horizontal scaling of the scales
of the mass
in comparison with their size.
Exactly.
Yeah, and directly in relationship with the charge, the electron, and the ionization energy that comes directly from it.
Exactly.
And profoundly, alpha comes from the dynamical geometry of the relationship between the electron and the proton.
Yeah. And the oscillating dynamics of a system that has an angular momentum and so on, and that really kind of it's another thing that emerges from these new physics, is that all of a sudden this need, I mean this relationship to Schrodinger's equation and so on, that we didn't have time to mention there, with the Poisson screening, which is in this paper, but we didn't have time to mention it. But there is relationships to like a more understandable nature of quantum physics, like a more, and it's beautiful, meaning it's much more, although it might disappoint some that it's like not so esoteric, it's much more mechanical in nature because fluid dynamics and so on. It's beautiful as it's like it has this amazing non-linear relationship to the rest. It's hard to describe. When you work with these equations every day, you get used to like thinking in that way, and you start to visualize these like quantum vortices inside quantum vortices inside and scaling and so on. But it's beautiful, and it really has deep meaning. So I look forward to sharing that stuff later on.
Another question from Constance. She's asking, can you describe mass in relation to time? I think we respond to this question showing that the rest mass of the proton is directly derived from the correlation time of the proton.
Exactly. So that's very good. It's a good question. And, we didn't kind of expand on it. I mean, if we wanted to dive into what is time, then we could. But
time is a circulation.
Is a circulation. Exactly.
Because we measure time when circulating around the sun.
Exactly.
When the Earth circulates.
When the Earth circulates and so on. and a hint on the papers to come, is the word circulation. So
little teasing.
Yeah, little teasing. But yes, the time correlates to an energy at a certain scale due to a coherent mode of the vacuum fluctuation in that scale. And I'm gonna really kind of stretch the bubble now, and so like take what I'm saying with a grain of salt. However, you can imagine that you can push that analogy of the coherent behavior of the Planck plasma to organizing systems, self-organizing system that eventually produce biological structures. And I know you've studied a lot of biology as well. because you've done a lot of biophysics, and William Brown as well, and so on. And so there's, like, remember, like, we're made out of protons, and those protons make up the cells. And because we've put things in boxes, this is biology, this is physics, doesn't mean that the universe has done that. And these forces that we can unify now, we can see that they can lead to, what we see at the biological level.
Yeah.
And so that's really, really exciting.
Yes, that was the next question.
I
don't know if you want to address this topic.
Oh, yes.
Maybe a question about the geometry. A question from Dizon, who is asking, why do the PSU arrange themselves in tetrahedral pattern? Is this a function of gravitational vectors alone, or does it include other factors?
Okay.
It's a question about the
geometry
of organization of PSU, maybe because of the fact that we have indicated.
Yeah, face-centered, cubic.
Exactly.
Yeah, well, it has to do with how spheres pack. And it has to do with how the different fields would triangulate to create, like, standing waves. And the geometry of those standing waves. And in
fact, we find this geometry in the structure of water, for example.
Exactly. Which, brings us back to biology, because all biology emerged from water.
The water, the most remarkable fluid in the universe, with remarkable properties.
Right.
And being like the nursery of stars in the middle of the galaxy.
Exactly. There's all kinds of analogy there that we can make. But of course, the analysis, the tendency when we do geometries to do an analysis in which the geometry is static. And that's not always appropriate, because really nothing is static, it's all oscillating. And so not only you have to consider, an average relationship of things as they circulate, as they move, as they're dynamic of things. So there's the local geometry that you could isolate. Maybe it would be, tetrahedral. I mean, the fact that the 64 sphere packing comes out naturally from Einstein field equation is interesting. When you apply it to the holographic mass solution, you find that 64, but it's a dynamic movement. It's not a static one, and so you have to keep that dynamic view in mind.
Like we saw for the quantum vacuum fluctuations, that can be seen as cycle of creation and annihilation. So we can imagine also that in addition to flowing, we have the creation, the annihilation. So it's a continuous process.
Dynamic, and with geometric constraints like sphere packing.
Yes.
Yeah, which would generate triangulation naturally, face-centered, cubic type of geometry, like cube octahedron and so on, which I studied in details in my earlier studies, because I felt that the geometry could really teach me something about the universe. It paid off with the holographic mass solution.
Yes, because it's an additional information. There is the information of the matter, but also the form itself has its own information. And
exactly.
We can see it in material science when you choose the right design for the material. You can enhance the mechanical properties of this material.
Of the material.
I'm thinking about the honeybee, for example, material.
Oh, right.
Type of structure which can support very high weight in one direction, but the other direction it's
not so much.
Not so much.
Right.
So it's a possibility.
Yeah. Okay, one more.
One
Yeah,
more.
the
Because-
last one, because
It's getting late
it's
over
getting
here.
late, yeah.
And I don't want you guys, if you're in the US, to blow your whole Saturday.
No,
Or
it's Thursday.
Thursday. Oh, sorry. Okay, I was a little ahead of myself. And so, but maybe one more.
Maybe one more. So one from John Carter, which is more a philosophic one, or maybe related to physics. Given that there are fluctuations in quantum vacuum, what is the cause of the fluctuation? Is consciousness a possibility, or maybe smaller scale, I would add?
A gradient.
A gradient, yeah. You know, the problem with the word consciousness is that is ill-defined.
Mm.
You know, what does it mean? You know, it doesn't say really like consciousness. What is that? I don't really have a way to like quantify it, say what it is. If you don't define what it is,
Mm-hmm.
then there's no mechanical way that I can say that consciousness. I would be, my tendency would be more the contrary, right? To see that the fluctuations of information transfer across the network is like a neural network of information that eventually leads to the network becoming self-aware. And that's why I like,
Because of the feedback.
because of the feedback, yeah.
Feedback loop.
Yeah, exactly. So I like the terminology self-awareness better because it implies some kind of feedback, some kind of mechanism, and then as well, really the idea, and I'm not being mechanistic or I'm just saying, you know, if you're gonna identify a source, you have to have some kind of description of that source that is defined. And so I'm not being reductive. I'm just saying, okay, imagine that the fluctuations that you're seeing at every scale, right? We're seeing that it has a decoherence pattern where the pressure drops. So when you have a density drop across scale, you have a gradient. And that gradient has a lot of energy in it, right? When you're going from ρ-vac, from quantum vacuum fluctuation to the universal density, you have a significant gradient, right? I mean, just to give you a comparison, like the gradient of a few degrees temperature change between the surface of the ocean and the air can give you a hurricane, you know, of incredible forces with millions of tons of water spinning and, you know, lightning coming down and, you know, everything going up in smoke. And this is just a little bit of a gradient in the density of the air. So imagine a gradient between the universal density and the Planck density. Wow, you got some serious dynamics. You got some serious energy density change. And why stop at the Planck? Our paper identifies the Planck as a cutoff value for a very specific time scale that has to do with the speed of light, right? That doesn't mean it's the end. That just means that in our universe, this is the fundamental pixel. But there's probably sub-Planckian, because the Planck is probably made of sub-Planckian little entities, right?
Like a fractal?
And yes, it might be a fractal, and then the universe might be part of a larger universe, right? And so on. So actually, this amazing beauty of infinite potential reemerges. And you know, when you find infinities in physics, it's like, oh no, how do I get rid of this thing, right? And it just kind of keeps emerging everywhere.
But cut off.
Yeah, where is the cutoff? Well, okay, maybe when you identify a cutoff, that's good. You can write physics on this, from this scale to this scale, and figure out how it works. But when you figure out how it works, when you figure out the scaling coefficient, when you figure out the scaling of these things, all of a sudden, if you figured it out in this thing, then you know it extends beyond that, and you refine the infinity, but in this case, in an infinity that you can write physics on.
Yeah.
So it's powerful. Yeah.
Yeah.
Okay.
Brilliant.
I think we should stop on this for tonight. I really appreciated all of you being present with us. Again, I apologize for the disturbance and the technical difficulties we had. I hope you enjoyed the presentation, and I really hope you can help us, you know, by talking to your colleagues and your friends and all this. We're going to set up a place where you guys can study the paper, see these videos, send your colleagues and friends there and family, and you know, have a discussion. So we'll have a forum that you can have a discussion on, and we're going to tell you how it's going with all of the and let's just peer review this thing all together, and we'll be presenting it, you know, for publication as well, and we can share, you know, that process with you, and let's grow together and learn together and evolve. And yes, go ahead.
And don't hesitate to share it to other physicists, because we want to have debates, to debate these ideas, to complete them, and to show how to apply them to other fields and to go deeper in our...
Exactly. You know, there's so much to explore and so much to complete. So in any case, for now, please take good care of yourself, and until we see you next, may the vacuum be with you. All right. Bye, everybody. Thank you so much.